Welcome to topology class. Today we will discuss how to get a topology from a neighborhood system. So last class we have discussed about neighborhoods and neighborhood systems. When you're considering a point X and the neighborhood system means we are considering all the neighborhoods of X in the topology. And we will say this collection of neighborhoods is going to be the neighborhood system. So from your last class, we have got a proposition, 2.5 proposition. That is, let X be a space, and for X belongs to X, and for X belongs to X, let eta of X be the neighborhood system, at X. Then we are having four conditions, right? Then I'm writing the conditions here because these conditions we require for proceeding with the next theorem. If U belongs to eta X, then X belongs to U, or 2 eta X or nx you can pronounce, no problem. For any U comma V in the neighborhood system, then U intersection V belongs to the neighborhood system. Third condition, if V belongs to eta X, and U is contained in V, then U belongs to eta of X. Fourth one, a set G is open in X if and only if G belongs to eta X for all X belongs to G. As said, G is open in X if and only if G belongs to eta X for every X in G. And the fifth condition, if U belongs to eta X, then there exists V belongs to eta X such that V is contained in U and V belongs to eta Y for all Y belongs to V. These things we have detailedly discussed in your previous class. So using this, we will prove that there exists a topology whose with respect to that topology, the interior will coincides with this neighborhood systems or its interior operator. So 2.6 theorem. 2.6 theorem. Let X be a set, X be a set, and and suppose for each suppose for each X belongs to X belongs to X, a non-empty family, a non-empty family, empty family, non-empty family, uh, nx of subsets of X, subsets of X is given. So a collection of neighborhoods of X are given, satisfying the four conditions, right? No, five conditions. Conditions that same 1, 2, 3, 4, and 5. And 5 in the above proposition. In the above proposition. Above proposition. Above proposition. Then there is a unique topology. Then there is a unique topology T on X such that for each X belongs to X, for each X belongs to X, nx or eta x coincides with the family of all neighborhoods of X with respect to this topology. That is, if a system of neighborhoods of X is given which will satisfy these conditions that we have mentioned above, then we want to prove that there exists a unique topology tau on X such that for each X belongs to our topological space X, our eta X will coincide with the family of all neighborhoods of X with respect to this top, with respect to this topology. Let us see how we can prove it. Proof. If at all such a topology exists, if at all such a topology exists, then by property 5, then by 5 gives us a clue for its construction. We let this topology is equal to set of all U subset of X such that this U belongs to eta x or nx for all x belongs to U. Okay, so we are selecting those subsets of x such that that subset is a neighborhood of each of its members, right? That's the meaning. I repeat, we are collecting those subsets of x such that they are neighborhoods of every point of that set and and claim that claim that this T is a topology. Claim that this T is a topology. So in order to prove this is a topology, we want to check the three conditions. First condition was empty set and the entire set belongs to this T. Now clearly empty set belongs to this collection. What's the reason? Because empty set is a neighborhood of each of its points, because empty set contains no points. So clearly we can write empty set belongs to this top. Next, what we want to show? X belongs to top. So to show that to show that X belongs to this T, note that for any x belongs to x, any x belongs to x, x belongs to nx by condition 3. What was that? A superset of any set is contained in is also a neighborhood, right? Since right since x is a superset of is a superset of any members of nx, since x is a superset of any members of nx, so x belongs to your collection T. Now we want to show that it is closed under finite intersection and arbitrary union. Now by property 2, what was that? If uv belongs to nx, then u intersection v belongs to nx. Shows that no need of by. Now 2 shows that this T is closed under finite intersections. While using 3, condition 3, it follows easily that because union is again going to be a neighborhood, it follows, or superset, right? It follows easily that this collection is closed under arbitrary unions. So we have proved that it is closed under arbitrary unions. So this implies your collection T, which implies your collection T is a topology on X. The topology on X. Now, now we want to prove that if at all such a topology is existing, then this collection Nx will coincide with the neighborhood system of X with respect to this topology. Now, with our definition of the topology tau, condition 5 means that for any x belongs to x, and u belongs to eta x, there exist open sets V, that is open means V belongs to the topology, such that V belongs to eta x, and V is contained in U. Since we have collected this U belongs to eta x, then V is contained in U. Now from 1, condition 1, we get x belongs to V, thus U contains a member of tau, U contain a member of T containing X, and therefore a T neighborhood of the point X, hence every member of your Nx is neighborhood of X with respect to T. Okay, so this is the first part. So we have proved that there exists such a topology which coincides with the neighborhood system of that topology. So what are the steps we have come across proving this? See, first of all, we are from the property 4. From the property 4, see this one. A set G is open if and only if G belongs to Nx for all x belongs to G. From this thing, we are having a clue for constructing the topology. That means you are taking the collection as the sets which is having that property. That is U subset of x such that U belongs to Nx for all x belongs to U. Now we will claim that this is a topology. For that we will show that empty set and x belongs to this collection Next, we will show that this collection is closed under arbitrary union and finite intersections. That using that property, we will show that this is a topology. Now we want to show that in this topology, the neighborhood system is exactly the NX itself. So with this topology definition, for any x belongs to x, there exists a u belongs to nx, there exists some open set v, right? So in order to make it clear, what it says. Suppose you got a x here and we are having lot of neighborhood systems. So let me make this neighborhood system. Suppose these are going to be your neighborhood systems. So lot of neighborhoods will be the x neighborhood, right? Lots and lots of whatever I am writing in dotted lines, all are neighborhood systems of x. Okay, now we are having x belongs to topological space. Now x belongs to this. Now inside there exists some open set. In this neighborhood also I can find an open set. Now this is my v, right? By definition of neighborhood, there should exist some open set which containing x and which is completely contained inside. So here, if I'm taking this as my n3, now in n3 belongs to, using another one, okay, you're having x belongs to eta x, right? Which implies x belongs to some n3 I am taken here, which is an element of your eta x. Now n3 is a neighborhood. N3 is a neighborhood means inside n3 there should exist an open set. That open set I am considering as this V. It's clear? So this V is contained in U. So instead of n3 I am having U. Okay. Now from 1 we get x belongs to V. Thus U contains member of tau containing x. Therefore this is a tau neighborhood of x. Conversely, now we want to prove the converse part. Conversely, let U be a neighborhood of x. A neighborhood of x with respect to a topology. Then U contains a member V of our collection such that x belongs to V and V is contained in U, right? But then this V belongs to neighborhood system of x. So by 3, condition 3, U belongs to neighborhood system of x because it is a superset. Thus, neighborhoods of x with respect to our topology are precisely are precisely the members of Nx for each x belongs to x. Hence the theorem. Hence the theorem. So what about the converse part? Conversely, what we want to assume? We want to assume U be a neighborhood of x with respect to tau. Then what we want to prove? Now this neighborhood is belongs to the neighborhood system. Then since U is a neighborhood, it should contain a open set, right? Let that open set be V. Now it is open means it belongs to the topology. So x belongs to V and V is contained in U. But this V then belongs to neighborhood system. So V belongs to neighborhood system means this U, which is a superset is also belongs to this neighborhood system. But the neighborhood system of X with respect to our topology is nothing but eta X itself. Okay, hope you understood today's class. I'm winding up the session here. Thank you for your patient listening. Thank you.